always to give a presentation for our PhD students. So please forgive me if the presentation will be too simple for some of you, but I want to make this presentation very interdisciplinary, just to show you the general idea standing behind the subject I want to talk about. So let me start from very fundamental statements, which you all know, obviously, that fundamental interactions between particles, as we know up to now, are well captured by the so-called standard model of fundamental interactions and elementary particles. In the standard model is constructed in such a way that we have some fundamental particles called quarks and leptons, which do interact via different forces, and these forces are mediated by particles, bosonic particles, called gauge bosons. The most famous, of course, is photon, which mediates electromagnetic interactions between charged particles, but we have also other particles, gauge bosons, which I will, in a few seconds, I will explain more deeply. And all matter we know is built from these elements. And the most common elements, of course, in our part of universe are neutrons and protons. So neutrons and protons are built from 3 quarks. And in the case of neutron, we have 2 down quarks, which are here, and 1 up quark, which is here. And in the case of proton, we have 2 up quarks and 1 down quarks. One thing which I would like to tell you here, and let me focus on the mass of neutron. As you see, the mass of neutron is almost 1 giga electron volt divided by speed of light. But if you sum up masses of 3 quarks, you see this mass of up quark is 2.2 and down quark is 4.7. It means that when you sum up the mass of these quarks, the mass of neutron is almost 100 times larger than the sum of masses of quarks which are forming neutron. It means that the tremendous part of mass of the neutron, and the same is for proton, comes from internal interactions in this particle. So interactions, binding interactions inside neutron and proton, and also kinetic energy, in fact, of these quarks is the dominating ingredient of the total mass of neutron and proton. So this is the side remark which I would like you to remember, because it is something not very obvious and commonly known. So the standard model, if we look on it more deeply, is can be divided to sectors. And standard model, when it was formed at the beginning, it was known that it describes electromagnetic interactions, which of course are composed from electric and magnetic interactions, but these both form electromagnetic interactions. And we have also weak interactions and strong interactions. Weak interactions and strong interactions are very short-range interactions, and they are important only on short distances between particles, creating nucleons and other other composed particles. Electromagnetic interactions are long-range interactions, and as I told you, they are mediated by photons. But it turns out at some moment that electromagnetic and weak interactions are in fact unified, and they are two different faces of the same kind of interaction called electroweak interactions. And these electroweak interactions are responsible for interactions between leptons. So when you remember, if you remember, we have leptons and quarks in standard model. So electroweak interactions are between leptons. Leptons do not interact via strong interactions. This is very important. Leptons interact only in electroweak sector. Strong interactions are really strong, the strongest interactions we know, but they are very short range, and they are responsible for formation of nuclei, and the strong interactions are present between quarks as well as quarks and leptons. And these strong interactions are mediated by gluons. This is the, you can think about gluon as some counterpart of something like photon, but in different scenario, and also there are different symmetries related to this, fundamental symmetries to these interactions. So we have gluons, which mediate strong interactions. We have photons, which mediates electromagnetic interactions, but photon together with W and Z bosons are responsible for mediation of electroweak interactions. You can think that photon is mostly responsible for electromagnetic interactions, and Z and W are mostly responsible for weak interactions. But as I told you, these two are unified, and in fact, there is some combination of them, but I don't want to go into details. What is important here is that this construction, the standard model we know at the moment is very experimentally relevant. What does it mean, experimentally relevant? It means that in high energy physics or in any experiments we can perform, in fact, we don't see any deviations from its predictions. We can understand forming of different composed particles like nuclei. We understand how they decay, and all these things decay, interact, and all this is well predicted by the standard model, and we don't see any fundamental deviations in the standard model. At this point, I would like to make a short note that maybe this is not true, what I said just a few seconds before, because few months ago, there was one experiment or one report of series of experiments related to the measurement of magnetic moment of muon. As you see, muon is the heavier counterpart of electron. So magnetic moment of the muon was measured, and this magnetic moment, is also the value of this magnetic moment is also predicted by the standard model. And at the moment, this experiment is the first and the only experiment we have in which deviations from standard model are possibly visible, I would say, in this way. Okay, so the experiment must be repeated in many different places in the world, but at the moment we think that this is the first place where the predictions of the standard model are in contradiction with experimental data. So we will see in the future how the story will go on, but maybe this is the first point where the standard model maybe is violated in experiment. But this is not the whole story about standard model, because in fact, in standard model, the table I showed you is not complete, because the table must be extended by antimaterial particles. In fact, the standard model describes not only the matter, but also antimatter. Antimaterial particles are exact counterparts of material particles, which have opposite sign of charges related to the interactions. So this is the, I don't want to go into details, but there is I would quote such a sentence, okay, is that existence of antimatter is a direct consequence of our requirement that quantum mechanics must be consistent with theory of relativity. As you know, at the beginning of 20th century, two fundamental theories in physics were born. It was quantum mechanics, which describes interactions between matter and fields on subatomic scales, and theory of relativity. So this theory of dynamics of material things traveling with high velocities, and this is about also the relativity of time and distances. All this you know, and these two, if we want to merge or to make the consistent quantum mechanics consistent with theory of relativity, the direct consequence of this requirement is that we need to generalize the Schrödinger equation, which is the fundamental equation of the dynamical equation of quantum mechanics, to the so-called at the first stage it was Dirac equation, but later to the formulation of quantum theory of fields. So to describe all the particles in terms of quantum fields, and this requirement that quantum mechanics must be consistent with theory of relativity leads directly to the prediction that if there is a particle which experiences an external field, think about electron experiencing electromagnetic field or electric field, then if quantum description of this electron interacting with electromagnetic field must be consistent with theory of relativity, then immediately it means that must exist corresponding particle, we call it anti-electron, which experiences the same field in such a way that it had opposite sign. So it means simply that this charged particle has to have opposite charge, electric charge. So, but of course, if we have quark which experiences interaction with some gluon, because it has its charge, it is called color charge, because strong interactions are related to color charge, then there must exist opposite particle, antiparticle related to this quark, which experiences interaction with the same gluon in such a way that it has opposite color. Okay, so this is the direct consequence of requirement that quantum mechanics is consistent with theory of relativity. It means that in standard model we have two two words. In fact, we have matter, which I tried to explain you how it works and how it is described in standard model, and we have antimaterial world, where we have particles experiencing exactly the same fields but with opposite charges. But you may think that maybe this antimatter particles are not existing because we don't see them. So partially you are right. However, let me show the following example related to the standard model. So as I told you, in standard model we have weak interactions, and these weak interactions are responsible, for example, for beta decays. So we have standard beta minus decay, in which neutron decays to proton and electron, and also some antineutrino. Okay, and this process is well known. It was discovered at the beginning of 20th century, and this process is very known, and it happens in nuclear physics. For example, potassium decays to calcium and electron. So during this decay, the beta particle means electron, is emitted from the nucleus, and the nucleus changes its composition. So number of neutrons changes by 1, and number of protons changes by 1, and therefore, in this case, potassium is changed to calcium nucleus. And it is good to know that free nucleon decays in few minutes to proton and electron. Of course, in nuclei, the situation is a little bit different, because these are no longer free nucleons. And proton is a stable particle which do not decay. However, it is known that there exists beta plus decay, which may happen in the presence of other nucleons. So, for example, in nuclei. And in this case, proton decays in opposite, the decay happens in opposite way. The proton decays to neutron, and during this decay, the anti-electron, positron, is emitted. For example, potassium in this beta plus decay decays to argon and emits anti-beta particle, so anti-electron. And of course, this decay is much less probable, because this is not the natural decay as it was in the case of beta minus decay, but this is the decay which can be present only in the presence of other nucleons. So it happens in the nuclei. It is the probability of this decay is very, very low. But if you think about our common things containing a lot of potassium, for example, bananas, then you can find that medium-sized banana emits 1 electron every 70 minutes. So 1 per hour, you have emission of 1 electron, anti-electron, from the banana. So it means that each banana is some kind of factory of antimatter. Just imagine that you have factory of antimatter in your home, and because these anti-electrons are simply emitted by our ordinary material, not antimaterial, but material things. So it means, and this decay is well predicted by the standard model, and it shows this example, but we have many of such examples. This example shows that even if you have ordinary matter, some processes are possible which changes the number of particles and number of antiparticles in these processes. So the number of particles and antiparticles is not conserved, because as you see here, as you see at the beginning we have one particle, and after this decay we have one particle as a neutrino, one part as neutron, one particle as neutrino, and one antiparticle as anti-electron. Of course, if you assign the numbers that particles are positive numbers, you count the particles with positive numbers, and you count the antiparticles with negative numbers, natural numbers, then of course the total number of particles is conserved, because here we have one, and here we have 2 minus 1, it's still 1. So, but the individual numbers of particles and antiparticles are not conserved. And here, let me make small digression about this decay, beta plus decay, because this beta plus decay was discovered by the daughter of Maria Skłodowska-Curie and her husband, Irene, and her husband, Frederick, and they studied this. Yes? Any question? Hello?
I think it was just unmuted mic.
Okay. So we have this, they studied this beta plus decay, and for these studies, they won Nobel Prize in 1935 in chemistry. And it is so the studies were published in this very famous paper. It is famous because it is well-cited paper, because this was the first paper about this beta plus decay. It was published in Nature in 1934. So as you see, at that time, 1 year after discovery, it was possible to obtain Nobel Prize. But what is my digression? My digression is that the same process, but for different nucleus, was studied at the same time by our Polish nuclear physicists, Ludwig Wertenstein and Marian Danysz, famous Polish physicist, Mariusz Danysz especially. They studied exactly the same decay, but for different nucleus, and they published their results exactly in the same volume of Nature, but few hundreds pages later. Okay, but it was the same volume, and it was, in today's terms, we can say it was parallel submission of the discovery of the same thing by two different groups. Of course, you know that they didn't win the Nobel Prize in chemistry nor in physics, of course. The only prize they won was the prize for Marian Danysz. It was Smoluchowski medal in 1969 for this discovery, and this is the medal. At that time, it was the most prestigious medal founded by Polish Physical Society. But they didn't obtain the Nobel Prize. So this is the digression. Digression can be even put further, because together with Ludwig Wertenstein and Marian Danysz and Michał Żyw, they had a fourth collaborator, Józef Rotblat. And Józef Rotblat is famous from his discoveries and his experiments with neutrons. And Józef Rotblat, you see his picture here. This is not a picture from a jail, but this is the picture, his photo from Los Alamos, because he was the member of this famous Manhattan Project. He was one of the scientists working there. And Józef Rotblat, after Second World War, was involved in, he was lived here in Poland. He was in Warsaw. You can even find Rotblat Square in Warsaw, Rotblat Square in Warsaw. But after war, he was working outside Poland, and he never come back to Poland. But he was involved to the anti-nuclear weapon movement after war, and he was the leader of one of these movements. And in 1995, he won Nobel Prize for peace for this movement and for working on anti-nuclear weapon statements at that time. So this is the small digression. It is, I think, it is worth to know that we have such a connection. So as I told you, matter and antimatter, as predicted by the standard model, is produced in equal amounts always. So if we have the individual numbers of material particles or antimaterial particles are not conserved, but the total number, when you sum up matter to antimatter with, of course, with this negative sign, it is conserved. And these conservations are well captured by so-called conservation principles, which are somehow accidental principles in a standard model, but because they are not, they do not follow from the symmetries of the model, like electric charge conservation, for example. Electric charge conservation follows from the symmetries of electromagnetic interactions. But there is a baryon number conservation and leptonic number conservations, which are not related to any symmetry of the standard model. However, standard model obeys their conservation. So, for example, if we think about some extensions of standard model, the simplest possible extensions of standard model, they predict some non-conservation processes of this baryon and leptonic number. So, for example, there is a prediction that proton maybe can decay to electron and pion, but this decay was measured experimentally. So, upper bound for this decay is that we know from experiments that it cannot be less than 10 to 33 years. So it is much more than the age of the universe. The same is with conservation of leptonic number. There are some predictions that leptonic number maybe in some processes don't need to be conserved, as predicted by these extended models of standard model. However, it was also measured in the experiments, for example, such a decay from germanium to selen, and then 3 leptons are emitted, 2 leptons and 1 antilepton, so the leptonic number changes by 1, and there is a lower bound for this decay, that this decay time cannot be less than 10 to 26 years. And as you see this it is quite interesting to note that these bounds are much higher than the bound measured for electric charge conservation, which I told you is related to the symmetry of the standard model, because here we have only 10 to 18 years experimental bound. So this symmetry is natural in standard model. It comes from the symmetry. This conservation is natural in standard model because it follows directly from symmetries of the model, and the bound for this is lower than the bound for these accidental conservations present in standard model. And as you see, standard model predicts these conservations accidentally, and it is well captured by experiments and confirmed by experiments. Again, small digression here. This is not full story about the standard model, because in fact, in standard model, there is one possibility which may happen in very, very high energies, that number of baryons and leptons is not conserved individually. So baryons can be, the number of baryons and number of leptons can change. However, this process were never, of course, experimentally captured, because it may happen in very high energies, and this is called Falleron solution of the standard model. If you are interested, you can go, you can follow this acronyms, Falleron. But it is only one possibility, but never experimentally proved. Okay, so we have full symmetry between matter and antimatter in the standard model, understood as a production in equal amounts, because there are some other things which are not related, which shows that there are some differences between matter and antimatter in standard model, but from the point of view of the amount of creation of them, amount of production, there is a full symmetry in the standard model. However, it is quite obvious, and you of course know, that there is a clear disproportion between matter and antimatter, at least in our observed universe. It is from different measurements of the background radiation and astronomical measurements, we know that there is a small difference between number of baryons and antibaryons. Of course, in our world, on Earth, this is the tremendous difference, because we don't observe, in fact, antibaryons. However, there is from the measurements it follows. So it is good to relate this difference of number of baryons to antibaryons to the number of background photons, background radiation photons, because this number is independent on the size of the universe. So even if the universe expands, then this number is more or less conserved in current. Of course, at the beginning it was not conserved, because photons and baryons were produced and annihilated but after decay of matter from radiation, this ratio is more or less conserved. And from these observations, astronomical observations, we know that it is something about 6 × 10⁻⁻⁻, this ratio. Okay, and if we assume that just after Big Bang, so just after the beginning, only radiation was present, then of course the standard model fails to explain this disproportion, because then, as I told you, the number of baryons and antibaryons, the total number of baryons must be conserved. So if at the beginning it was 0, then and the production rate of baryons and antibaryons is the same as predicted by standard model, then of course at any moment this ratio should be equal to 0, but individual ratios as predicted by standard model should be 10⁻⁻20. But of course, number of baryons and number of antibaryons should be the same. So there is a fundamental disagreement between these astronomical facts and the standard model. And the question is how to, this is a mystery, of course, which has to be somehow explained. It is one of the arguments that the standard model cannot be the final fundamental theory of fundamental interactions, and then we need to find its extensions. But to find its extensions, we need to have some experimental evidence that standard model is violated in some experiments. So as I told you, we don't have any deviations from standard model. We can, at most, at the moment, we have one deviation related to this muon magnetic moment, and maybe this is the first point where we should look for extensions for standard model. But of course, we need to find some more places where the matter and antimatter behaves differently and in contradiction to the standard model. So this is why we need to find a way to measure somehow, to experimentally verify the symmetry between matter and antimatter. If you want to know more details about this proportion in nature and how it is possible that it may happen, I would like to ask you to refer to so-called Sakharov conditions. Sakharov in 1967 formulated 3 conditions, requirements, which must be fulfilled by the theory to have a possibility to predict the how this proportion can be built from theoretical grounds. And standard model is not does not fulfill one of the Sakharov conditions, the first Sakharov conditions, in fact. Okay, so the best way to study the difference between matter and antimatter is to study bound states of, this is one of the possibilities, is to study bound states of matter and antimatter, material and antimaterial particles. So the simplest scenario is to imagine that we can create some kind of hydrogen-like atoms composed from matter and antimatter. So as you know, hydrogen is the simplest possible atom. Its binding energy in the ground state is a little bit more than 15 electronvolts. And the mean distance between proton and electron is so-called Bohr radius. It is around 50 picometers. Okay, but imagine that we are able to substitute the electron by antiproton. Then, of course, such an atom is still, from the theoretical point of view, at least on this electromagnetic level, it looks like hydrogen, but with different reduced mass. And in fact, it is called protonium. In fact, protonium can be produced in experiments. And for protonium, as you see, the binding energy is much, much higher because it is more than 1 kilo electronvolt. But its lifetime is quite large because it is around 1 microsecond. The mean distance between proton and antiproton in protonium is of the order of 50 femtometers. So it is 1,000 times smaller than the Bohr radius of the hydrogen. And it means that the proton and antiproton in this bound state are so close to each other that the dynamics of proton and antiproton is strongly affected by strong interactions, which are very short, and they are present only with the baryonic particles. So proton and antiproton, because they are made of quarks, they do interact not only via electroweak interactions, but also via strong interactions, and the strong interactions strongly affect this system. So this kind of atom, protonium, is very good candidate to study strong interactions with atomic precision, because this is atoms, so we can here apply many different methods known from atomic physics, spectroscopic methods of atomic physics to study excitations, for example, in this protonium. And then by studying the influence of the shifts of the levels in protonium, we can study strong interactions between proton and antiproton. But imagine that we can also substitute, instead of substituting electron, we can substitute proton by anti-electron. Then we have positronium, so the bind state of electron and anti-electron. This is the lightest hydrogen light electron. Or we can substitute proton by anti-muonium, so this heavier counterpart of electron. And these systems, these bound states, are also very interesting because they are purely leptonic systems. As you see, there is no hadron here. There are no quarks. So this system, interactions in these systems are related only to electroweak interactions. So these are very good candidates to study electroweak sector of the standard model, because we know that they are completely decoupled from the strong interactions. And these atoms were also produced experimentally, and their lifetime is so long that they can even undergo chemical reactions. It is possible to create, for example, molecule of positronium or positronium-chlorium molecule. The same is with muonium. So these are real atoms which are not present in the table of elements, but they can undergo chemical reactions, and their chemical properties are well known. And finally, you can substitute proton by antiproton and electron and anti-electron, and then you get antihydrogen, which is the exact counterpart of hydrogen in the antimaterial world. So by studying properties of antihydrogen, you can compare their properties and look for the differences between hydrogen and antihydrogen. And now I would like to ask, how much time do I have more? 15 minutes or?
Yes, 15 minutes.
Okay, that's great. I will finish in 15 minutes. So, but you can think also about more complicated exotic atoms. Imagine that you are able to substitute one of the electrons in heavy atom by antiproton. Then this system is completely different from other atoms, because antiproton is 2,000 times heavier than electron, and therefore his contribution to the configuration of these electrons and is tremendous, and it completely changes properties of this atom. And this is very good candidate to study the influence of hadronic matter to the leptonic cloud, for example, made of electrons. So this is also very good platform for testing the standard model in this intersection between electroweak and strong interactions. So let me tell you a little bit more why it can be interesting. Let me focus on these antiprotonic atoms. So in the simplest scenario, antiprotonic atoms are created in different way. That antiproton substitutes innermost electron, the key shell electron. And in this case, the antiproton is more or less at the same distance from the nucleus, but because of the mass ratio, which I told you, it is 2,000, the principal quantum number of this antiproton is of the order of 40, because the innermost electron is 1, the principal number is 1, so it is about 40. And because of antiproton mass, the its energy, its binding energy is different. As you remember, for hydrogen, we have energy of several electronvolts. In the case of antiproton, orbiting on this orbiting as a hydrogen-like, in this hydrogen-like atom, because this outer electrons do not play any role in this case. This energy is around 25 kiloelectronvolts. So it means that this energy is much, much larger. It is thousands times larger than the energy related to electrons. And why it is interesting? Because now this antiproton is on this orbit, and it undergoes the excitation, spontaneous de-excitation, as normal electrons do when they are highly excited. And then we can observe this emitted photons, but these emitted photons will have energies of kiloelectronvolts, not electronvolts. Okay, so these are very high X-ray photons, high energy X-ray photons. And at some moment, this antiproton is so close to the nucleus, then that strong interactions start to affect these transitions, and therefore we see clear deviations from the predictions of these electromagnetic transitions. And finally, the antiproton annihilates on the surface of the nucleus. But these experiments can be done, and as you see, these high energy photons were observed, and their positions, their energies, fit quite well to the energies predicted by standard hydrogen-like Rydberg model. But of course, for small decays, there are small for small principal quantum numbers, there are deviations. Everything is explained in terms of interactions, strong interactions between antiproton and nucleus. And why it is interesting? Because when you think that the nucleus is not spherical, then of course it is known also from purely electronic atoms. Then we know this quadruple deformation of the nucleus may force transitions not between states having angular momentum different by 1, but different by 2. These transitions are forbidden if the nucleus is spherical. However, if it has some quadruple deformation, then such transitions are possible, and they were observed for electrons as well. However, in this case, because this transition energy is so large, in the case of antiproton, is so large, because it is in kiloelectronvolts, it may happen that this energy is exactly or almost exactly equal to the excitation energy of the nucleus. And then we have very nice resonance between electronic states of orbiting antiproton and nuclear states related to the spin of the nucleus and deformation of the nucleus. So we can measure nuclear properties of nuclear matter, and by electronic measurements or electromagnetic measurements of antiproton undergoing decay in the so this is one of the tools giving us opportunity to measure with atomic precision the nuclear matter. Okay, and this is indeed possible because, for example, here for tellurium, as you see, the transition energy for antiprotonic tellurium is hundreds of kiloelectronvolts, and first excitation of the nucleus energy is almost perfectly fitted to the transition of the antiproton undergoing transition from n equal 9 to n equal 7. But to do this, but of course, to make all these experiments with atomic precision, you need antiprotons. So now let me tell you how these antiprotons are produced, because as I told you, anti-electrons are produced in quite natural way with beta plus decay. But to have antiprotons, you need to have something more complicated, because antiprotonic mass is so large that it cannot be produced spontaneously as anti-electrons. So this is the map of CERN. And the most famous, of course, is this LHC accelerator, where all this fundamental research are done on last. For example, the most famous in the last decade was finding Higgs boson. But there is also the small facility there. It is called antiproton deaccelerator, where antiprotons are produced, stored, and experiments are done. How it is done? These antiprotons are produced from protons, which are accelerated in the small accelerators here. They are accelerated to quite large energy, and then instead of transferring them to this large LHC accelerator, some of them are transferred here, and here this highly energy protons simply hit the iridium rod, and during this collision, there is non-zero probability that the additional pair of proton and antiproton will be produced. And all this is under such a control that every minute 2 to 13 protons is produced in this 10 to 7 antiprotons is produced here, and then they are collected by electromagnetic forces. These antiprotons are collected, and then they are sent here to the accelerator, which decreases the energy of antiprotons, and then they are decelerated to the kinetic energy around hundreds of kiloelectronvolts, and then they are distributed to different experiments. In this way, 5 million of antiprotons is delivered every 2 minutes to different experiments in this facility. And the most, let me say something about these experiments. So one of the experiment, BASE, for example, is known from precise measurement of magnetic moment of antiproton and compared to a magnetic moment of proton. And as you see, their measurement shows that these two quantities are almost perfectly identical. And this is what I called atomic precision. You see, the number of digits is tremendous. And it is, so from this point of view, proton and antiproton have exactly the same properties. They also measured the ratio of electric charge to the mass of antiproton and proton, and they compared these two numbers, and the comparison is also atomic with atomic precision, because the deviation, if any, is on 12 digits on the 12 digits of this ratio. There is another experiment, alpha, which compares the transitions in hydrogen and antihydrogen, so electronic transition. And as you see, these transitions are almost, and they measured, for example, particularly the transition between S1 and 1s to s states, which are affected by lamp shift, so corrections from quantum electrodynamics, and they compared the same transition for antihydrogen. And as you see, comparison is here, and as you see, there is no difference simply between hydrogen atom and antihydrogen atom. And I think my time is finished, so I will just, in 2 sentences, I will tell you also about our experiment. This is EDGE's experiment, and the main goal of this experiment is to find not the deviations between matter and antimatter in standard model, but to find the possible deviations between matter and antimatter when they interact with gravitational field. So the main the main goal of this experiment is to perform atomic precision experiment of falling of the antihydrogen in the Earth gravity, and compare with the same falling of the hydrogen atom. So it is so we just simply want to have antihydrogen which will fall down, freely fall down in the gravitational field of Earth, and then we will measure the acceleration of this falling. So it will happen something like that. That first, antiprotons will be delivered to the experiment. Antiprotons will be captured in an electromagnetic penning trap. Then positrons will be added to this antiprotons. Positrons will produce positronium. Positronium will interact with antiprotons, and finally we will get antihydrogen, which will fall down in the gravitational field, and we will measure its acceleration. So this is the general scheme of this experiment. And okay, so this is, I think, everything I wanted to say. Thank you very much for your attention.